Good day, and welcome to our webinar on troubleshooting techniques for AC induction motors, brought to you by CFE Media and Technology and sponsored by Lenza, Parvolux Electric Motors, and SCW Eurodrive. Joining us today will be Michael Lyda, Motor and Drive Engineer with Advanced Energy Corp. I'm Kevin Parker, Editor of Plant Engineering Magazine. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. The learning objectives of today's presentation include a review of motor management best practices, tips on how to increase process reliability, tips on how to reduce energy costs, and an exploration of Vfd Basics and benefits. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit exam tab option at the top of the screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. Here are some tips to help you get the most from today's webcast. If you experience issues with your slides or audio, refresh the browser or click the Refresh Media button under the presenter's picture. Control the volume on this webcast by adjusting the volume on the computer or on the webcast platform. For technical problems with audio or slides, click the question mark at the top right-hand corner of the screen to access system checks to try before contacting us. If a technician is needed, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask questions of our speakers. The live Q&A session will begin once the presentation concludes. To download the completion certificate, a PDF copy of the presentation, and additional resources, use the Event Resources tab on the left-hand side of the screen. Those documents will also be available with the on-demand version of the webcast. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. Before beginning the presentation, we invite you to view the following videos, provided by our sponsors, Lenza, Parvolux, and SCW Eurodrive. At the conclusion, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned.
Getting stressed out by how complex automation can be? Lean on the experts from SCW Eurodrive and check out our Movikit automation modules. Movikit is a collection of pre-built software modules for many common motion control applications, ranging from simple drive functions like speed control and positioning, all the way to complex functions like camming and even kinematic robot control. Movikit makes it easy for engineers of all skill levels to do their own automation. We handle the complex programming part, and you simply enter your parameters and go. Shorten your startup time with configurable automation and motion control functions. No need to waste your valuable time with complex automation programming. Check out Movikit, the pre-built software modules from SEW Eurodrive.
Parvalux Electric Motors is a leading global manufacturer of geared motor solutions, chosen by manufacturers to power hundreds of diverse applications. From industrial cleaning equipment to materials handling equipment, Parvalux provides the reliable power for a range of workplace applications. Our team of application engineers will work to meet any requirement, including fully customized solutions.
Welcome back. I'd now like to introduce today's speaker. Michael Lyda started working for the Advanced Energy Motor Lab in 2010 as a co-op student. After completing an engineering fellowship with Advanced Energy, Michael moved into the Motor Lab coordinator role in 2013. With extensive testing experience in the lab, Michael then moved into the laboratory director role in August of 2019. His efforts today are devoted to motor system testing development, research, and training on a wide range of applications. Michael is also a member of the Advanced Energy commercial and industrial team, participating in energy assessments and recommending energy conservation measures at regional facilities. Michael received his bachelor's degree in electrical and computer engineering with a minor in mathematics from North Carolina State University. Michael, welcome to today's webinar, and please go ahead.
Thanks, Kevin, and also thanks again to CFE Media for giving me the opportunity to present today. And just to reiterate, if you do have a question at any point during the presentation, please submit those or general comments in the Ask a Question box window. I'll respond to as many of those questions as I can at the end during our designated Q&A session. Throughout the presentation, we'll also be launching poll questions to gather your input, so please keep an eye out for those and share your feedback. So today we'll be presenting on electric motor management and variable frequency drives, or more commonly known as VFDs. This information is intended to help you develop or improve your motor management system and generate energy savings for your organization or even your clients. For those of you that may remember me or recognize me, I did give a presentation earlier in the year with CFE Media on motor troubleshooting. Some of the info from that presentation will also be covered early on in this presentation. If it seems repetitive, just hang in there with me because we'll be getting into the new material rather quickly. First, I would like to say a few words on Advanced Energy. We may have worked with some of you on the line before, but for those who aren't that familiar with Advanced Energy, I wanted to take a minute to introduce ourselves. We are a nonprofit energy engineering firm created in 1980 by the North Carolina Utilities Commission. We were charged back then to investigate and implement new technologies for distributed generation, load management, conservation, and energy efficiency. Over the last 4 decades, because 2020 was our 40th anniversary, we've worked closely with our clients as an independent resource for unbiased technical expertise on commercial and industrial, residential, electric vehicles, motors and drives, and renewable initiatives. Anyway, that's enough about Advanced Energy. Let's go ahead and get started with the content. So, why are motors and drives or electric motors important? Motor-driven systems are estimated to account for approximately 50% of all electricity generated in the world. Motor-driven loads likely account for a large portion of the energy bill at your facilities. Having an effective motor management system and taking advantage of energy savings opportunities with variable frequency drives can save you a lot of money over time. I presume that's why most of you have joined the call today, or maybe you're like me, you need one more PDH or one more CEU before the end of the year. Either way, glad everyone's here. Hopefully you can participate. So we'll be given the presentation in 4 sections. Those are listed here: motor basics, motor applications, motor management, and finally the section on variable frequency drives. We could easily spend all the time on any one of the topics. We have about 45 minutes, so we won't be going super deep into any one subject. The material also isn't meant to be deeply technical since we do have a pretty wide-ranging audience. We do have some good technical examples, though. If you do have deeper technical questions, just reach out to me afterwards. I'll supply my email address at the end. And also the presentation recording, I think, will be available for everyone afterwards. All right, so first we'll start with the motor basics. So what is an electric motor? Electric motor is a rotating apparatus that converts electrical power to mechanical power. Voltage and current are the inputs, and torque and speed are the outputs. It's very likely that you interface with electric motors many times a day in your everyday life. At home with your refrigerator, your washer and dryer, maybe even your HVAC system, in your car, power windows, windshield wipers, and then of course at most of your jobs, pumps, fans, compressors, chillers, boilers, many other things that we could list off. There are many different types of electric motors. Today, we'll mainly be talking about induction motors, although, when we talk about the motor management techniques that we're going to discuss, they're going to apply to nearly all motors. You'll see induction motors listed on this slide in the top left. In the top left, induction partitions off to single-phase and polyphase, or namely three-phase motors.
We seem to have lost Michael's
Single-phase
audio.
motors would typically be found in residential or smaller agricultural applications. And three-phase motors will be found in industrial and even larger commercial applications.
You can hear him on your line, so that's fine. We'll just continue.
So induction motors have been around since the 1800s, but that doesn't mean that they're really old news. In general, they have simple, straightforward operation and are somewhat easy to produce at high volumes. They're also very rugged and typically pretty reliable. That's why they've lasted since the 1800s. Next, we're going to go over the different components of an induction motor. On this slide, we have rotating components from left to right. In the picture, we have the shaft, the rotor, which is painted red, the rotor paddles and balancing nubs, which are shown in cast aluminum, and then the component labeled number 4 is the fan, which is, for this motor, is plastic. Sometimes you will see other materials for the fan. Plastic is probably the most common. Next slide, we have housing components, end bells on both sides of the machine, the bearing housings and stator housing, which are both painted orange here, the cooling fins on the outside of the motor, the junction box where the motor terminals are found. It's hard to see, it's kind of in the back of the motor on this picture. And then finally, labeled number 9 will be the fan shroud, and that's used to safely guard the fan during the motor operation. Final slide of components, we have the fixed components. So shaft seals, stator windings, stator laminations, and bearings. Of course, bearings are probably the most influential component on motor life, and we will definitely be getting into that more later on down in the material. Next, we'll see a few examples of motor nameplates. I'm not going to spend much time on this, but just to give you an idea of what you may be looking for, some of the more common nameplate specifications will be listed on the following two slides. So here we have very important parameters on the nameplate that are involved in the sizing the motor for your application and matching to your incoming power requirements. These include horsepower, speed, voltage, and current. Each motor should also have a specific model number and serial number from the manufacturer that designates it from all of its other products. Here are a few more parameters that you might find on the nameplate, including service factor, also called short-term overload factor, frame size, which is generally standardized across this industry, the motor industry, insulation class, which indicates the maximum allowable internal temperature, the full load running efficiency, the power factor, which generally is a ratio of real power used to total power generated by the utility, and then finally NEMA design letter. NEMA is the acronym for the National Electric Manufacturers Association. It's a trade organization of electrical equipment manufacturers in the United States. Electric motor manufacturers participate in NEMA to standardize various performance factors across the industry. The design letter is one of those. This isn't just for motors. NEMA isn't just for motors, but for many different types of electrical equipment. Next, we have a display of a standard induction motor compared to a generally higher efficiency motor. These cutouts are on display at our lab in Raleigh, if anyone on the line ever comes by for a tour. This slide is more representative actually of older induction motor design versus newer, since all covered induction motor products sold in the U.S. today are required to be NEMA premium efficient. A few things to note: the difference in the amount of rotor and stator laminations, what's painted red on the picture, and also the fan size. But now I'm looking at the slide, we can't really see the fan on the efficient motor, so I guess you'll just have to take my word for it. Sorry for that. Generally speaking, an efficient motor will have more copper, more steel, and most likely a smaller fan than a less efficient counterpart, although this is just generally speaking. The increase in steel and copper make the motor heavier by weight, and more material means more money. So more efficient motor, typically more expensive, even if you just look at the material aspect. Efficient motors generally will operate cooler. One common question that folks may have: how do you have a device that operates cooler when it has a smaller cooling fan on it? The answer to one of the answers: a more efficient motor will likely have a lower operating current due to lower resistance in the windings. This means the I²R losses, power losses of the stator will be less, and then of course lower losses leads to higher efficiency overall. So that completes our section on motor basics, and now we'll transition into motor applications. A few of the topics we'll be covering in the motor applications section are recommended operating conditions, the selection and proper sizing of motors, and lastly, we'll review the application affinity laws. First, let's talk about ideal operating conditions for your motors. Ideally, you'll need balanced voltage from your utility. For instance, if you have three-phase 480-volt supply at your location, those phases should be balanced to within at least 1% or better. The more out of balance your phase-to-phase voltage may be, the more detrimental to your motor's efficiency and also long-term reliability. One thing you may notice that most low voltage motors are rated for 230 volt, 460 volt, or 575 volt operation, even though typical low voltage distribution levels are 240 volt, 480 volt, or even 600 volt. You may be wondering about the difference. The 10, 20, 25 volt difference accounts for the voltage drop in the distribution lines into your facility and then within your facility. Slight overvoltage at your motor leads is all right. It's not generally that much of a problem. Heavy overvoltage can be a problem. But what you don't want to have is undervoltage at your motors. So if you were to check voltage at your motor terminals and see voltage under the nameplate rating, definitely want to troubleshoot to determine the cause. Secondly, your motor should be aligned to the load to have as little mechanical vibration as possible. This is achieved typically by good shaft alignment. There are various tools out there, so having a laser alignment tool may be a good addition to your toolbox, especially if you do a lot of motor installs in-house. Otherwise, verify that your service provider is using some type of precision alignment tooling. Thirdly, you want a clean environment for your motors. I understand this is kind of, engineer talk. This isn't always possible given the application. But generally, just make sure your motor is kept free from contaminants entering the motor. If the motor has a fan, if it's a fan-cooled machine, keep the fan shroud unblocked so the air can properly move across the motor so you get good cooling. You may even want to clean the fan blades every so often if you're in a high dust particle area. Just, of course, make sure your motor is de-energized before you were doing anything like that. Lockout, tag out. Fourthly, the motor's ambient temperature is very important. If the motor nameplate states a maximum ambient temperature, you should respect that. If you see the ambient temperature consistently above the rating on the motor nameplate, then it's likely the motor should be derated for that application. You can always reach out to the motor manufacturer for more details, or maybe, if you consistently run in the motor at too high of an ambient, you may be dealing with a failed motor earlier than expected. And then finally, the last point on this slide, motors are optimally designed to be ran at their rated load. So for instance, if you have a 10 horsepower motor and you run it at 5 horsepower, the efficiency will be poor and the power factor will be very low. Both of these things are going to cost you on your energy bills in the long run. Poor efficiency, low power factor. Common problem across the industry is motor oversizing. Purchasing folks, not to say there's anything against, but purchasing personnel sometimes may believe if the application calls for a 15 horsepower motor, for instance, purchasing a 20 horsepower motor may make the motor last longer, but this isn't typically the case. All right, so before we get into some maintenance procedures, we have our first poll question. So I'll encourage everyone to participate. You'll have about 1 minute to answer the question, and results will be displayed on the screen. Also, just to remind everyone, keep in mind you can ask questions via the Q&A box, and we'll try to get to those at the end of the presentation. If we don't get to your questions then, we'll get back to you afterwards within the next few days or a week at the max. All right. So thanks to everyone for participating in the poll question. Looks like we did get some wide-ranging answers, but the main response was D, all of the above, and that's the correct answer. Routine motor maintenance should include each of the items that are listed in A, B, and C. Vibration analysis and tracking over time, infrared thermography to find hotspots, and motor circuit analysis to check for any insulation degradation. So here's a review of a slide from where we left off prior to the poll question. Heat kills motors. You know, for anyone who did participate in the webinar earlier in the year, maybe you remember that. That was kind of my main message, heat kills motors. You know, if heat kills motors, this begs the question, what causes motors to heat up? And so high ambient temperature, blocked fans, blocked cooling vents, overloading the motor above rated load, and then, of course, power quality issues at the motor terminals. Some typical power quality issues, you know, it's a very broad term, but some of the typical issues include unbalanced voltage, single phasing, you know, dropping a phase, or relatively close in proximity nonlinear loads that will lead to voltage and current distortion. You know, known commonly in the industry as harmonics. Next, we'll cover some operation and maintenance best practices. As a maintenance personnel, for any of those here that are maintenance folks, one of your main goals is definitely to prevent failures. When you do all you can to limit and prevent the failures, definitely for motors, it's likely you'll get less questions from your managers and so on, which is typically good news. At least it is for me. Downtime can be very costly, and at times your job may depend on how quickly you can bring a process back online. So limiting downtime with proper motor maintenance can alleviate some of the stress around this. First, we'll talk about the mechanical conditions listed. Even if a motor is aligned well at installation, various factors can lead to misalignment during operation. If the motor itself starts making some loud or strange noise, shut it off, verify the alignment. You can verify parallel alignment with a simple straight edge. To check for angular misalignment, you might need a telescoping gauge, which, you know, not everyone will have in their standard toolbox, but they can be ordered very quickly. They even come in packages covering many size ranges. So, you know, what I have is a pack of 5 or so telescoping gauges that cover many different motor sizes. Additionally, you want to keep the motor bearings well lubricated. Bearing failures are the leading cause of motor failures. And, you know, we'll see that in a second. We've got a nice chart to show you. Grease the motor bearings at the recommended manufacturer interval, and be sure to use the proper type and amount of grease recommended. Grease both the drive end and non-drive end bearings, and make sure the grease nubs are clean before adding the grease so you don't get contaminants in the grease. Most motors today use Polyrex EM. You know, you can't assume that for all motors. That's just typically the most common grease for new motors. So good to keep some tubes of that around if you don't already have some. Also, keep your fans checked for obstruction. Make sure no stray debris get inside the fan shroud at any time. And then for some electrical problems, good to keep a multimeter around to verify your phase-to-phase voltages. Check for the balanced voltages if you have access to the motor terminals. If you have the motor on a contactor, which is likely, check the contactor terminals periodically for carbon or contaminant buildup, especially if this is an on-again, off-again application. You know, think conveyors or press. Also keep an eye out for arcing at the contactor or pitting over time. You can also use an ammeter to verify amperage at the motor leads if you have access to those. Once you have the amperage readings, you can compare to motor nameplate full load amperage. Additionally, with the motor de-energized, you can check winding resistance of the motor. The motor should have balanced phase-to-phase resistances. If the motor is hot and maybe you want to compare winding resistance to the original manufacturer values, then you'll need to let the motor cool down for quite a bit to have an apples-to-apples comparison. If the resistances are out of balance, then you may want to run some dielectric tests with a Megger or something similar. And of course, with all of this, only properly trained personnel should be completing the maintenance procedures and using any of the equipment that I've mentioned. So next we see the leading causes of failures taken in motor failures. This is taken from Institute of Electrical and Electronics Engineers website, IEEE. We see bearing failures very high on the list due to the issues mentioned earlier. Also, listed here, insufficient lubrication, even excessive lubrication, too much grease, the wrong grease, parallel angular misalignment, vibration, or overheating of the bearing. Next leading cause of motor failure is stator winding issues. This is characterized by short circuit or open circuit. These will be caused by repetitive overloading and subsequent overheating of the motor, causing some issues in the windings. External conditions are right there with the winding issues. These include heat, humidity, contamination problems. A few other causes of failure are listed, but not the typical cause. Also, here it's worth mentioning that your motor build quality will absolutely play a major role in motor reliability and long-term life. You can do, as a maintenance personnel, you can do everything right, but if the motor has quality issues from the factory, it can still fail prematurely. Here's a general overview of what we've discussed in this section. So one of the most basic but very useful preventative maintenance techniques is to use your senses. Look for worn parts, discoloration of motor leads and wires. Feel the motor for strong vibration and excess heat on the case. Smell for strange odors or burning smell coming from the machine. And then finally, listen for excess or unusual noises. You do want to keep the exterior surfaces and cooling passages clean and clear. Keep your bearings properly lubricated. Keep the motor alignment very good, and any belts or chains at the proper tension amounts. Also, keep the motor terminal lugs at the proper tightness, and on down the line at your bus bar or motor control center, keep those at the proper tightness as well. What you don't want is have your motor terminals or motor wires falling out of a VFD, for example. On the right side of the screen, you see some more advanced preventative maintenance measures listed, including the vibration analysis, infrared thermography, current signature analysis, and remote monitoring. Of course, if you have that capability. A lot of folks won't have remote monitoring. Next, we'd like to give you a few examples of motor loads before we get into the energy savings measures portion of the presentation. Generally, there are two types of loads, centrifugal and linear. Centrifugal includes the spinning inertial loads, where the load will tend to decrease with speed. Some examples are pumps, fans, and blowers. Linear loads are more direct loads like crushers, elevators, or conveyors. And typically, linear loads require some constant torque application independent of the speed. For the remainder of the material today, we'll be focusing mainly on centrifugal loads. Here, we present two types of motors used for these loads, a fixed speed motor and a variable speed motor. For a fixed speed motor, output air or liquid flow, on your fan or your pump, must be regulated mechanically by valves or dampers. There are quite a few innate losses in this type of system. However, if you can use a variable speed motor for the same system, the output air or liquid flow can be regulated by motor speed. This provides potential energy savings based on the affinity laws. And we'll be getting into some of that in a few minutes when we discuss variable frequency drives. So we reviewed some motor basics and motor applications. Now we'll move into topic number 3, motor management. So first off, a few numbers to get you in the mindset of motor management and why it's important. The average motor consumes at least 50 times its purchase price in electricity usage over its lifespan. The motor purchase price accounts for only 2 to 3% of the motor's lifetime cost. A small percentage is used for maintenance and upkeep, but the overwhelming majority of a motor's lifetime cost is its electricity usage. Approximately 4 out of 5 motors that fail are repaired instead of being replaced. This is a very broad number, varies widely depending on the size of the failed motor. Also, only a small percentage of end users consider energy costs when looking at new motors or making the decision to repair or replace a failed motor. We estimate it at 12%, which is very low. Hopefully, by the end of the webinar, this number should look like 100% for everyone listening. Due to those reasons and many others, every organization that uses motors should definitely have a set of guidelines for managing their motor population. So, what are the main components of a motor management system? There are 3, purchasing, operations and maintenance, and lastly, making the decision of repair versus replace. What are the benefits of a good motor management system? This is the key question. The benefits are energy savings, cost savings, increased production, shorter downtimes. What do all those things mean to you? Again, happier management, like I said before, means less pressure on you. In my job, happier management, less pressure on me. So, how hard is it to create a sufficient motor management system? Really, it's not that hard. Come up with good guidelines for your 3 main components. So, for purchasing, develop purchase specifications. Normalize what brands you use. Specify model numbers. Consider lifecycle costs instead of only looking at initial costs. Purchase backups for your most critical machines. Build up a spares inventory. For operations and maintenance, we've already really covered that. Just follow the practices that we discussed earlier. Perform routine maintenance on your motors. Focus more of your time on critical motors with high usage rates. For motor repair, you want to use repair shops that you trust. Now, I would also recommend using a certified repair shop. They should hold some sort of third-party quality repair accreditation. Then you really have a third party, you can really feel confident in, the work that's going on at the shop. And also, just like for purchasing, develop motor repair specifications. If you're using a certified shop, they can likely help you create a repair specification. Honestly, if they won't help you do that, you might want to find a different shop. Next, we have an example. I mentioned before that only 2 to 3% of an electric motor's life cycle cost is in its initial purchase price, and the remaining 97+% is in electricity cost. This example compares life cycle costs between a 75 horsepower electric motor and a standard small car. Notice the purchase price, annual usage, efficiency for the motor or miles per gallon for the car, fuel cost, and lifespan. We use all these variables to calculate a life cycle cost for each product. Notice the initial cost of the vehicle is 4 times that of the electric motor. Also notice the life cycle cost for the motor is 6 times that of the vehicle. So this all adds up to some pretty hefty electricity bills for the motor, which I'm pretty sure if you have anything to do with the energy at your facility, you're already aware of. So next, we're going to dive a little deeper into each of the 3 components of the motor management system just described. So step 1 is to create your motor purchase policy. Standardize your purchasing, which makes it easier to order the products you need, takes less time overall. Purchasing staff need to be properly trained, so initial cost isn't the only factor in the equation. What we just saw from the example, initial cost has very little impact on life cycle cost. You may want to pre-qualify your vendors and in some cases even perform testing. Our lab in Raleigh kind of specializes in that. Don't really want to go into too many details on some of the specific projects, but that's the kind of work that they do. Additional item to look at in purchase specs is motor efficiency. So motor efficiency is a very important factor in motor management. So important, in fact, you can count on the federal government to help get involved in this decision. Many electric motors these days are efficiency regulated and have minimum efficiency requirements that must be met for legal distribution in the states. Not all, but many. The most up-to-date efficiency requirements are called Nema premium levels. Each manufacturer that wants to distribute in the U.S. is required to prove their motors meet these efficiency levels before they begin selling. The problem is the government sets regulations but does little to enforce the regulation. So once a manufacturer has met the minimum requirements, there's very little they need to do regulatory-wise to stay in compliance. I said all that to say this. The efficiency number listed on a motor nameplate isn't necessarily what it actually operates at. It could be higher, it could be lower. From my experience, most of the time it's going to be lower. It's always good to perform quality checks on your motor suppliers to ensure motor build quality and running efficiency aren't degrading over time. We're going to spend a few minutes now discussing motor repair, which is the third and final component of the good motor management system. Step one with your motor repairs is to ensure your vendor is providing quality repairs. Similar to developing a purchase specification, you should develop a repair specification. You'll see many items listed in the slides that can be added to your repair specs. As I said earlier, use accredited repair shops. There are many third-party quality repair programs out there, including ESA accreditation, SKF certified, Green Motors Initiative, AEP Motor, eMotor Rewind, and even Advanced Energy's own Proven Efficiency Verification Program. All these programs are good, but each has its own distinctions. The goal of any accredited repair program is to ensure your motors are being repaired to the highest quality and the process being used is standardized and followed time in and time out with every single motor. Speaking of the quality repair motors, we have an example here showing what can happen when quality control procedures aren't followed. This chart shows two performance curves for a 10 horsepower 4-pole motor. Nameplate full load efficiency for the motor is 91%. We see the orange line, which shows efficiency when the motor was repaired, including bearing replacements with top-of-the-line motor bearings. The bluish-green line shows efficiency when the motor was repaired, including bearings that were of lower quality and not properly greased. You see quite the gap between the efficiency performance of both motors. It's vital to make sure that your repair vendor is not making mistakes like this, or you'll be losing money and electricity when you put these motors back into service. One thing to consider with the repair vendors, they're very happy to have your business, and they'll typically keep records for motors they've repaired or reconditioned for you, so they can be very helpful in your management system tracking. Keep an open line of communication with your vendor and utilize them as much as you can. Once you have a motor management system in place, keep track of your motor failures and track your energy costs versus production. You can use these numbers to update and improve your policy as you see fit. This isn't a one-time exercise. This is something you want to constantly be improving to maximize your reliability and savings. So generally, when you're purchasing motors, use lifecycle costs instead of just initial cost. Develop and use purchase and repair specs so that you get the best motors for your application and the highest quality repairs. And finally, utilize strategic preventative maintenance techniques to upkeep your motor population and extend useful life. So now we're into our fourth and final topic, variable frequency drives. So like I said at the beginning of the presentation, we're not going too technical here. We just want to give you a good base knowledge around this topic. This content is broken into 4 areas: VFD Basics, identifying potential applications to add VFDs, energy savings calculation example, and some application issues involved with VFDs. It looks like maybe I'm, talking a little bit too much. We probably won't have time to go through the calculation example. I want to reiterate, though, that Advanced Energy, we're certainly not selling any motors or VFD products. So when we talk about VFDs, we're not just recommending them. We also want to list you the disadvantages along with just the advantages. So first off, there's quite a few names for VFDs. Here I've listed a few. They all mean the same thing: variable speed drive, variable frequency drive, inverter, just drive. So what is a VFD? VFD is a device used to adjust the speed of an electric motor. Grid power can be connected to the input terminals of the VFD, and then the output terminals of the VFD will be connected to the motor. The VFD can be used as a medium to control motor speed and torque by varying the frequency and voltage seen at the motor terminals. We used to use some old speed control methods prior to VFDs, here listed: dual speed machines, gearboxes, pulleys, belts, soft starts, baffles. What are the advantages of VFDs? Speed control. It's easy to start and stop the motor. No inrush current at the motor terminals, so less stress on the motor windings. Improved process control for precise applications, especially when you add encoder feedback in your VFD package. High-quality VFDs will have a high power factor at all motor loads, since the capacitors in the VFD are offsetting the inductance of the motor, and of course the energy savings potential. Some disadvantages of using VFDs are additional capital investment. You may have to ask the boss for more money. My experience doesn't always go well. VFDs also add harmonic distortion to your system due to their capacitive nature. One other thing, you may experience nuisance tripping in your application if the VFD isn't programmed or sized correctly. And lastly, the VFD could actually reduce motor life. So generally, what does a VFD do? It takes in the three-phase AC power, converts it to DC, then converts back to AC through the form of a pulse width modulated or PWM signal. It has an AC to DC rectifier on the front end, and then a DC-AC inverter on the back end with a DC bus in between the two. VFDs utilize IGBTs for the fast switching capability. So when you walk into a facility, you may hear some high-pitched audible noise if VFDs are being used. This is called the switching frequency or carrier frequency, and is in the kilohertz range, maybe 2 to 20 kilohertz for standard commercially available VFDs in industrial applications. Of course, not all VFDs are designed like this diagram, but just the simpler ones. So what applications work for VFDs? Centrifugal loads like pumps, fans, and blowers, throttled flow processes, and variable processes. These days, new air compressors are very popular VFD applications. Any boiler or chiller feed water pumps are very good opportunities, and of course, fans all over the facility are good opportunities. Also, applications with high annual operating hours. If you have higher operating hours, then you have more time to capture energy savings and offset the cost of the VFD itself. Also good to target larger motors, again, for quicker payback to offset the initial cost. Once you've identified potential motor applicants, dig a little deeper to determine the best candidates for a more in-depth analysis. If you've done, a motor, what we call a motor survey of your facility, you'll capture a lot of this information. Look at the estimated, or better yet, exact run hours, and we would recommend using, looking at all centrifugal loads with operating hours over 6,000 hours annual usage. So next, we're going to look at 3 different applications and compare the validity of adding a VFD. First, we look at a poor VFD candidate, a very highly loaded application. You may ask, why shouldn't we add VFDs to highly loaded applications? The VFD itself does use some energy. If you put a VFD on a motor and the motor is running near full load, You're just going to add unnecessary power to the circuit and actually raise your electricity usage. So adding a VFD doesn't make sense here. Second example, we see a moderately loaded application. Most of the operating time is spent around 60 to 70% load. This presents a good opportunity to slow the motor and capture some energy savings based on the affinity laws. And finally, with our third example, we have a moderate to low loaded application, even some loading below 50%, but still with high operating hours overall. This is an excellent candidate for adding a VFD and presents a great opportunity for significant energy savings. Like I said, we had a calculation example. Unfortunately, I've talked a little too much. We're not going to go through the example. A few last slides here about VFDs. There are some disadvantages. I would like to spend a few minutes going over the issues and what you can do to mitigate those. Some well-known application issues include the reflected wave, which we'll get into more in a minute, and bearing effects, including fluting, grease blackening, and potential increased motor failures. How does this happen? Well, motor bearings typically present the path of least resistance for high voltages coming from the VFD that get induced across the motor shaft. The voltage will reach a level to overcome the grease layer in the bearings, then shaft current will discharge. This is called fluting. We have some pictures in the next slide of the grease breakdown and bearing fluting. If we're doing an in-person training, we could have some hands-on examples to pass around the group. So now getting back to the reflected wave. Because of the pulse width modulated signal the VFD is sending to the motor terminals may actually see a peak voltage of 3 to 4 times the rated voltage of the machine. Higher quality VFDs find ways to mitigate this, but not all of them. The issue becomes especially bad when you have very long leads between the VFD and the motor, which is very common in industrial facilities. You may have a control room on one end of the plant where VFDs are housed that are feeding motors all across the facility. This is not good news for the motor windings. So how can we mitigate some of these issues? The bearing issues can be solved by using insulated bearings. You may also want to look at purchasing shaft grounding systems or grounding brushes. These are items that you can get from your motor repair vendor. When we talk about insulated bearings, this is something to request from your distributor when you purchase a motor or when you get it repaired. How do we mitigate the harmonics and reflected wave issues? One method is straightforward. Use shorter cables between the VFD and motor. Although, as I previously said, this isn't always possible. You can also purchase optional line reactors or load reactors with your VFD, and in some cases, they may come with it. There are also filters available that basically add inductance to the system. Adding filters and reactors can bring your harmonic distortion down to much more reasonable levels, but you need to weigh the pros and cons. In summary, VFDs can be very beneficial in speed control, process control, eliminating high inrush currents to your motor, keeping power factor high at all loads, and adding energy savings potential. However, some disadvantages include the additional capital investment, the added harmonics to your system, possible nuisance tripping due to incorrect programming, and even potential reduction of motor life. VFDs aren't right for every application. Screen your applications well before making the move to add a VFD. All right, so that concludes our content. Quick review. Today we covered the motor basics, motor applications, motor management, and variable frequency drives. I have listed a few references here. If you're working around motor testing, IEEE 112, standard 112 is very good, mainly for three-phase machines. IEEE standard 114 for single-phase machines. General motor knowledge and specifications, you can use Nema MG1. I call it the Motor Bible. And then for motor repairs, you see the last standard listed, ESA AR100, and that one actually has a new revision as of this year. Feel free to reach out to me directly via phone or email for follow-up questions or general discussion. I welcome any of that. And I guess at this point, I'll go ahead and turn the presentation back over to Kevin. I appreciate your attentiveness, and thank you.
Well, thank you, Michael, and I want to apologize to everybody for a couple of little technical glitches we had here. We still have close to 400 people on the line, so that proves, if nothing else, that content is king, because I thought that was a great presentation with some great practical information, Michael. We've got a whole lot of questions, and we don't have very much time, so Michael is going to have an assignment, homework assignment. We're going to try to get him to answer some of your questions, and we'll post them online with the archived version of this webinar. We do have a few questions here that we could probably get through real quick, kind of speed dial through. Michael, is air conditioning required for proper operation of a VFD?
Just like motors, the ambient temperature in the room, wherever your VFD is held, is going to be important. So just respect the ambient temperature that's on your VFD nameplate and make sure you're not exceeding that room temp where the VFD is stored.
Another question, inverter duty versus inverter ready motors. I am finding engineers writing specifications that are sometimes conflicting.
Yeah, this is an interesting question. Inverter duty, when we talk about motors that can be operated with a variable frequency drive, that's where we talk about inverter duty. They will be, valid to run the motor across a, full speed range listed on the motor nameplate at whatever variable torque range listed on the motor nameplate. Inverter ready, when you talk about what motors are regulated in the United States, if you put inverter only on the motor nameplate, you don't need to have that efficiency regulated. And so, inverter duty versus inverter ready, definitely need to spec out the differences. What is inverter duty? What are the variable torque and constant torque requirements at what speeds versus inverter ready? Maybe inverter ready means that you have some certain class insulation. It's something that should be looked at. I think it's a good point. I'm not sure I did a great job of answering that question, but.
Well, I'll be happy to give you another chance sometime in the near future. Another question, is there a software tool for efficiently figuring real power consumed by a motor?
I'm not sure. Software tool for real power consumed by a motor. I mean, we, in our lab, we use National Instruments data acquisition, and we're using LabVIEW software. But certainly when you look at, various instruments, you can buy various instruments. I won't list any other manufacturers, but you can buy instruments where you can track instantaneous power at the machine, and you get the voltage and current and power factor.
All right, great. That just brings us right to about the end of our time. So like I say, we'll post the answers to some of your questions on the website as soon as possible. But that's all the time we have for questions today. I want to thank Michael for participating in today's events, and I want to thank our listeners for attending. We hope it suited your purposes. For more information, go to the website links noted in the interface. I'd like to thank our sponsors for attending for today's webcast, and that includes Lenza, Powerlux Electric Motors, and SEW Eurodrive. And now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it as we use this information to improve our webcast. On behalf of CFE Media and Technology, thanks, and we'll see you next time.